Okay, let's take a look at lesson 4.8, L'Hopital's rule. You may find it, some people call it hospital's rule. Some people spell it with an S, but L'Hopital, French. So we'll go with that, what our textbook goes with. L'Hopital's rule is a technique we use to apply to evaluate limits, limits that have indeterminate forms, right, that are produced by quotients, products, subtractions, powers, right? And then we find a way, a trick, I guess you would say, it comes from, and it can be verified with a proof, right? But it's a way for us to evaluate functions that have these indeterminate forms. And so as you go through the examples in the book, you see the different indeterminate forms. Like previously, we evaluated the limit of sine x over x using geometry, looking at the graphs of sine x and x very close to 0. And you see they're identical graphs, and hence we come with a geometric argument that it equals 1. But using and applying L'Hopital's rule, which we'll find somewhere here, right? L'Hopital's rule in the case when you end up with 0 divided by 0, which we cannot compute, right? We end up with this definition here. So I want to make sure you pay attention to the notation, that you keep proper notation as you write your limits using the derivatives, right? And so it turns out magically that the limit of a function divided by another function is equal to the limit of the derivative of the function divided by the derivative of the denominator function. And then there's your proof as you go through it. Again, math majors, it's fun to go through and see kind of how this works out, how it simplifies algebraically, as you end up with the definition of derivative in this notation here. And hence you end up with L'Hopital's rule. And so we have these different cases, 0 divided by 0, and you can go through that. I'm just going to look at a couple of, again, just showing you all in one, not that one. There it is from our homework here. Of course, you have these videos that you can go through to look at the different versions of it. But I think the most important piece, again, it's important to know when it's allowable, right? Which conditions must exist to invoke or apply L'Hopital's rule. And so here are the indeterminate powers. There are several indeterminate powers, right, that sometimes come up when you're doing your work. As you end up with 0 to the power 0 or infinity to the 0, right? 0 over 0, right? We had these infinity divided by infinity. So you have these other indeterminate forms. So just, it's important to be aware of them. What happens when we end up with those scenarios? Okay. As you go through your indeterminate forms here. Okay. And then of course you have some of my homework help, hopefully to support you in some of that work, right? So let's just look at a couple of examples. I sent a link out on Pronto to question 4.7, but that link can be taken to other ones. And so here's again just an example of, here's a polynomial to a polynomial. We already know the rule. Take the, we have, when you plug in 1, take a look what happens, right? You get 0 over 0. And you just take the derivative, right? Take the derivative of the top and bottom. But notice the notation. I keep my notation. You have the indeterminate form. And then now when I plug in 1, you see it about 2 over 5, right? So looking at examples like that as we go through, let me pull some other ones here. There's the sine x over x, which we've done. How about the square root of x minus 4, right? Let's look at that one. So you can see again, you get 0 over 0 in this case. And then if you take the derivative, okay, if you take the derivative, you'll see it's 1 minus 0 on top, and then you have 1/2 square root of x, right, minus 0. And so then that simplifies, and you can plug in 4. So it's magic kind of that comes up. It kind of L'Hopital gets its importance can be minimized with graphical representations and things. And so this again works for trigonometric functions and exponential functions. So let's look at number 10 here. You can see you end up with some weird looking stuff here as you go through it. e to the negative infinity is 1 over e, which 1 over is 0. So you end up with that 0 over 0 again. And so when we look at how to go ahead and take the derivative of this one, again, you end up with something kind of strange looking, and then you simplify the algebra and you get 0 over 0. And so sometimes you can apply the derivative again, right? It's an application. Then you can apply the derivative one more time, and then you take the derivative. In this case, you get infinity over infinity. And then you get through kind of an iterative process until eventually you can then evaluate the limit. So take a look, an interesting one to look at, its length of what happens as you go through it. And of course, there's some, again, on this link here to L'Hopital's rule, we have a lot of other kind of examples to look at, not just the examples you can run through. Again, just a nice set of different problems. X to the X is a classic one, but a nice set of problems here for you to kind of look at here. So I'll include that link also.